Imagine floating in an endless ocean of pitch-black space, where not a single star shines, no galaxy twinkles, and no ray of visible light exists to illuminate the vast void. There were no vibrant glowing nebulae painting deep space in radiant colors. Neither bright cosmic beacons nor warm stellar light existed anywhere across billions of light-years. This was not the empty moment before the Big Bang, this was the universe hundreds of thousands of years after its grand birth. For nearly 200 million years, our cosmos was plunged into a quiet, mysterious era known by astrophysicists as the Cosmic Dark Ages. A time when space was filled only with vast, cold clouds of neutral hydrogen gas expanding silently in total, suffocating cosmic darkness. How did this vast dark void transform into the radiant universe of billions of glowing galaxies we see today? What dramatic physical events led to the ignition of the very first monster stars in cosmic history? Today, backed by groundbreaking observational data from NASA, the European Space Agency, and the James Webb Space Telescope, we explore the epic story of the cosmic dark ages. To understand why the universe fell into total darkness, we must travel back to 380,000 years after the Big Bang. At that critical moment, cosmic temperature dropped to around 3000 Kelvin, allowing free electrons to bind permanently with protons to form neutral hydrogen atoms. The primordial plasma fog cleared, releasing the cosmic microwave background radiation, the oldest relic light measured by Planck and WMAP satellite missions. But as those primordial photons stretched into invisible infrared and microwave wavelengths due to expansion, space faded into pitch darkness. The universe entered the cosmic dark ages, an era dominated by vast gas reservoirs of 75% hydrogen and 25% helium. During this epoch, the neutral hydrogen gas quietly emitted radio signals at a precise wavelength of 21 centimeters due to quantum atomic spin flips. There were no heavy elements like carbon, oxygen, silicon, or iron anywhere in space. Chemistry as we know it did not yet exist. The entire cosmos was a cold, featureless gas desert expanding uniformly without any internal heat source or stellar energy. Yet, hidden beneath this silent dark sea, an invisible giant was quietly pulling the strings of cosmic destiny, dark matter. According to peer-reviewed astrophysical models published in Nature and Science, dark matter made up the vast majority of cosmic mass. Because dark matter interacts only through gravity, it began clumping together long before normal gas could, forming massive invisible gravitational webs. These dark matter halos served as the invisible scaffolding, drawing neutral hydrogen gas into dense cosmic nodes across millions of light-years. Milestone 1, the gravitational collapse of pristine gas clouds inside dark matter halos. Over tens of millions of years, gravity patiently compressed huge concentrations of hydrogen gas into the centers of dark matter halos. Without heavy elements to cool the gas efficiently, primordial clouds could only radiate energy away through fragile molecular hydrogen vibrations. Consequently, gas clouds had to grow enormously massive, hundreds of times the mass of our Sun, before gravity could trigger inward collapse. As core pressure and temperature escalated to tens of millions of degrees, nuclear fusion ignited at the heart of these gas giants. Approximately 100 to 200 million years after the Big Bang, the very first stars in universe history ignited. Known as population 3 stars, these colossal celestial monsters were pure hydrogen and helium behemoths, shining millions of times brighter than our Sun. Their intense blue-white ultraviolet radiation pierced through the surrounding darkness, ending 200 million years of total cosmic silence. These giant stars lived fast and furious lives, lasting only a few million years before consuming their nuclear core fuel. Milestone 3, the epoch of reionization and the creation of early protogalaxies. High-energy ultraviolet photons from population 3 stars began stripping electrons from neutral hydrogen atoms, carving out glowing ionized bubbles. This transformative era, verified by NASA space observatories as the epoch of reionization, gradually made cosmic space completely transparent. Because population 3 stars were so massive, they died in spectacular parainstability supernova explosions, leaving no black hole remnants behind. These colossal explosions seeded deep space with heavy elements like carbon, oxygen, silicon, and iron for the very first time. Enriched by heavy elements, subsequent generations of smaller stars coalesced into primitive irregular protogalaxies. These early galaxy seeds merged under gravity, initiating the cosmic assembly line that birthed spiral galaxies like our own Milky Way. Today, humanity stands at the golden frontier of unraveling the cosmic dark ages thanks to NASA's James Webb Space Telescope. Equipped with ultra-sensitive infrared NIRCam and NIRSpec instruments, JWST can detect light shifted across 13.5 billion years of expanding space. Recent JWST discoveries have unveiled surprisingly bright early galaxies existing near redshift 10, challenging classical cosmological models. Observational data confirmed by Harvard-Smithsonian scientists provide direct empirical evidence of how light conquered the primordial dark void. Studying the cosmic dark ages delivers a profound perspective on our origin and place in the universe. Without those ancient population 3 stars igniting in the dark and sacrificing themselves in supernovae, the elements forming planets and human life would never exist. As astronomer Carl Sagan famously declared, "We are a way for the cosmos to know itself." Every atom inside your body, the carbon in your DNA, the iron in your blood, was forged in the stellar furnaces that ended 200 million years of dark solitude. Future radio telescopes built on the far side of the moon will soon listen directly to 21-centimeter signals from the dark ages, opening the final cosmic frontier. Understanding the dark ages reminds us of the extraordinary journey from primordial void to conscious intelligence gazing at the starry night sky. Thank you for joining us on this voyage through the cosmic dark ages. Farewell, and see you on our next exploration into the wonders of space. Before the first stars ignited, the cosmic background temperature dropped steadily as space continued expanding exponentially. Quantum fluctuations from the lamellar inflation era left subtle ripples in the density distribution of primordial gas. These microscopic ripples grew under gravity, forming gravitational valleys where gas concentrated into giant cosmic webs. Astrophysical supercomputer simulations at CERN and Harvard show that the first protostars formed singly or in small binary pairs. These population 3 stars were so hot that their surface temperatures reached over 100,000 Kelvin. Ionizing radiation swept across intergalactic space like cosmic wildfires, transforming neutral gas back into plasma. Stellar nucleosynthesis inside these monster stars created oxygen, carbon, and silicon at unprecedented rates. Instruments on JWST such as NIRCam have detected galaxies born just 300 million years after the Big Bang. Humanity's journey to understand the dark ages is a testament to the power of science and curiosity. The darkness of the past holds the key to understanding the luminous universe we call home today.